everyone! So we're going to look at homework 10.8 right now. This homework is about energy levels in the atomic spectrum. So for this one, energy in an atom can be determined by the difference between energy levels. A has the largest difference between the energy level it started at, 4, and ground level. So A must be the highest energy level. Then D, then F, then B. In fact, the length of these lines is proportional to how much energy that electron has. And when the electron moves from a high energy state to a low energy state, it emits a light wave. Sometimes we call these light waves photons. So you'll hear me use those two words interchangeably, and on Monday I'll help you differentiate between the two of those. So, our electron moves from a high energy state to a low energy state and emits a photon. Well, that photon is light. And we know for light that the more energy you have, the more frequency it must have. Think of the analogy of like shaking a magnet back and forth. If I have a really high frequency, I shake the magnet really fast, well, you put in more kinetic energy, so that light wave has more energy. And that's why our ranking for these two parts is identical. However, wavelength is inversely proportional to frequency. We know from the wave equation that since the speed of light is constant, that if wavelength decreases, then frequency increases. That inverse relationship is why this order is the way it is. Now, a bit of logic and a bit of colors that you're going to have to know. You are responsible for knowing the 7 sections of the electromagnetic spectrum in order from low energy to high energy. But that also means you should know the spectrum's visible spectra, Roy G. Biv, from low energy to high energy. If one of the jumps is red, that must be the lowest energy one, and the lowest energy was C. Violet was the highest energy one, so that must be A. Now, lots of questions on this model. So many questions that I'm going to try and do a drawing over this as we go. So, in order to figure out which elements are in the mixture, I need to line up every element of the unknown with another element. So, let's take this line here. It looks like it's about a 420 nanometer line. That matches up with helium's line. I'm going to put this here, and maybe I'm going to make it a different color. And like magic, it looks like all of the lines that are in helium are also the same color lines that are in the unknown. So helium must be one of the elements that is in that mixture. Now, off the top of your head, I don't expect you to know that 550 nanometers is green. And off the top of your head, I don't expect you to know that 650 nanometers is red. But I do expect you to know the approximate range of the visible spectrum. It's about 400 to 700 nanometers. 400 nanometers would be a really, really hard to see violet. 700 nanometers is so red, it's starting to stretch into the infrared. So, it looks like there's at least 3 other lines, 4 other lines that are not in helium. That must be from a different element. So if I line up this one right here, it looks like that second element must be hydrogen. So let's fill in those colors. And done. Now I've got all the hydrogen lines lining up. I see this cyan color lines up. I've got this middle-y orange color, a regular red, and then a red that's starting to get into the infrared spectrum so we can't see it. So, in short, how to use Model 2 in order to determine which elements are in a mixture is pretty straightforward. See which bright lines, which colors in the spectra line up with which elements that are in the unknown mixture. Bringing it back to Model 1, every atom has its own energy levels. So it will have its own colors that it emits when it's excited by temperature. So if I have these 4 gases, Each of those bright lines represents one of these energy transitions, and since scientists do know which elements match up with which colors, we can use that to identify which elements might be in a mixture. In fact, when I was a little bit older than you guys, when I was a sophomore in college, I actually did this as part of an internship in Rocky Hill, where we would like burn different things, and then I'd be able to use a special telescope, kind of. We'll call it, yeah, something like that. A special telescope that basically breaks that light up, and then a computer program tells you what elements are in the mixture of gas as you light this thing on fire. So in Model 3, now we're trying to combine Model 1 and Model 2 into one coherent picture, trying to connect what's happening with energy levels inside an atom with the colors you see if you excite that atom by making it really, really hot. So we've got this gas tube that's being discharged. Lots of electricity is running through it. The tube has hydrogen in it, and hydrogen has specific spectral lines. Every time we light hydrogen up, we can use a diffraction grating. We can use diffraction to spread those light beams apart, because remember, the different colors end up making interference patterns in different places. So for this, we were looking at the 4 different colors that show up in the visible part of the hydrogen spectrum. This picture right here in Model 3 is basically what would it look like if I took Model 1 and tried to make it look more realistic. N equals 1, the ground state, would form this lowest, inside, closest to the nucleus, most stable state of an electron, and all the others would be excited states. But even that's not really what they look like. Model 1 is easy to draw, so that's why we draw it that way. Model 3 is closer to accurate. And the O physics simulation is even more accurate than that. So notice for this that my lowest energy state, N equals 1, hey, this looks like it has a node and an antinode, 2 of them. N equals 2 looks like it has 1, 2, 3, 4 nodes and 4 antinodes. Guys, thing to note here, a really neat mathematical model, is that same node and antinode constructive interference pattern that you get with waves also happens with particles. We'll talk about that more on Monday. So let's go to what we're doing right now. We were given as part of this problem that all of the states end in transition level 2. Energy level 2 is the energy level we're looking at. And since we need to emit light, the electron needs to start in a high energy state, fall down, and end up in a low energy state. I want you to think about this as like a ball rolling down a hill. It starts with a lot of potential energy, and at the bottom, it has kinetic energy. The problem with that analogy, though, is that the electron doesn't have kinetic energy at the end. Right? So what we need to do to account for that change in energy is the electron needs to emit light, and the light has energy equal to this change in energy level. So let's do it. You can do this by color, if you can see the colors here, but the violet one, which matched up with, spectral line A, in order to produce a violet light, went from 6 to 2 in its energy states. This blue-violet, that matched up with B, so that would be from 5 to 2. This, I think it's called on the sheet blue-green. I call this color cyan. You're going to hear about it more next unit. It's important. Energy state 4 to 2. And as you're going, red should be my lowest energy difference here. Record the wavelengths. So as I was going through the simulation, I matched up the color, violet, with which energy level it was at, 6 and 2, wrote down the wavelength, and I calculated frequency just using the wave equation. These are all light waves, so they travel at the speed of light. their wavelength was known. If you end up with the wrong power of 10, it's probably because you forgot this second parentheses here. 3B you could answer without doing anything, without opening the simulation and doing any calculations. Because remember, you are responsible for knowing off the top of your head that violet is the high energy color. So violet is the highest energy color. You could also argue it's because it has the largest frequency, and frequency and energy are directly proportional, or that it has the shortest wavelength, and wavelength and energy are inversely proportional. All of those arguments would work. Right? Oh, I suppose a fourth argument to be made there is it's going from a high energy state to a low energy state, so this would be the largest difference in energy. That would also work. So 4 different ways you can justify this answer. Okay. Now, from 6 to 2 was violet light. So if that electron went all the way down from energy level 6 to energy level 1, that would need to have more energy than violet. It must be ultraviolet. Ultraviolet literally means above violet. Okay? Which brings me to the last question. With the last question on this sheet, we've got the difference between absorption and emission. And the trick is, these are the same process, but in reverse. Absorption is when light hits an atom, so the electron gets excited and moves up an energy state, whereas emission is when this excited electron falls down, so then light is emitted. They need to be the same energy by conservation of energy. This difference in energy from 3 to 2 is the same as the difference in energy between 2 and 3. So, same amount of energy. Okay? So, best of luck. Have a good night, guys.